So today we're talking about inverse functions, and specifically we're going to look at inverses of quadratic and radical functions. And first here, I just have a function f of x, and I have some ordered pairs, some points on that function. In my task here, I want to find the inverse of that function using those points. So all that I need to do is switch my x and y values to get my inverse. So let me go ahead and do that. So now my x's are going to be 4, 1, 0, 1, and 4. And my y's are going to be -2, -1, 0, 1, and 2. Okay, now it's time to graph these. And I'm just going to make a rough sketch. First, I'm going to plot f of x. There's those points. And if I were going to connect them, I would get the quadratic parent function. So what about its inverse? Let me plot those in blue. We still have 0, 0. And in fact, this inverse looks a lot like f of x laid on its side, doesn't it? Just kind of like that. So this is the inverse of my function. So here's a question for you. Think about it and then pause the video. Is f of x a function? Is the inverse of f of x a function? What do you think? Pause the video and think about it for a minute. So we would say that f of x is a function, but that its inverse is not a function. For f of x, each x only has one y, but for the inverse of f of x, some of the x's have two y's. In fact, most of the x's have two y's. So how could we change the domain of f of x in order to make its inverse a function? Well, the problem here is that f of x is not a one-to-one function. That means that while each x value only has one y value, the x values don't each have a different y value. So like both -2 and +2 have 4, right? When we reverse our x and y values and those y's become the x's, that results in a relationship that's not a function. But we could fix that by restricting our domain to just these values. Then when we look at our inverse, it also is going to be a function because it'll only contain those values. See, right up there. So if we were just to restrict our domain of f of x so that it only includes x values that are greater than or equal to 0, we would only be looking at this part of the graph that I'm highlighting yellow. And considering our inverse, we would only be looking at that part. So then both the inverse and the original function would be functions. So in order to make the inverse a function, we need to be sure that our original function is a one-to-one function. And if it's not, we need to just restrict its domain in order to make it a one-to-one function. So now we've got a basic picture of how the inverses of a quadratic function might work. So let's see if we can take the steps that we used in the last example that we looked at with the table of values and use those to find the inverse of f of x is equal to 5/10 x squared. So our function currently is not one-to-one. We know that it is symmetric about the y-axis. So we want to just restrict the domain so that x is greater than or equal to 0. Now, when we're working with a function like this, where we've been given an equation, what we want to do is interchange our x and y values. So currently, my equation says y equals 0.5 x squared. Because remember, f of x is the same thing as y. It's just a y in disguise. So now I'm going to switch my x and my y. So I'll write x equals 0.5 y squared. And now I want to solve for y. So my first step will be to divide both sides by 0.5. And that gives me 2x equals y squared. Then to solve this, I just take the square root of both sides. And I end up with the square root of 2x is equal to y. And that's the inverse of my function. Now let's talk about the domain of this function. Where will it be defined? Well, I can't take the square root of a negative number and end up with a real value. So that means this is only going to be defined where the square root of 2x is greater than or equal to 0. In other words, just like the domain of my original function, the domain of the inverse is going to be x such that x is greater than or equal to 0. So let's check this and see if we got it right. First, I'm going to check it by finding the inverse of my original function. So that means I'm going to find the square root of 2 multiplied by my function. See, I'm substituting f of x in place of x in my inverse. So that's the square root of 2 times 0.5 times x squared, which is going to end up as 1x squared. And the square root of that is just x. And that's what I wanted. When I take the inverse of my original function, I should end up with x. It works the other direction too. In this case, I end up with 0.5 multiplied by the square root of 2x squared, or 0.5 times 2x, which is also x. Now let's look at the graph of this function. You can see that it's symmetric right across the line y equals x. Here's my original function, f of x, and here's its inverse. So now we have three ways to see that it's right. First, we found the inverse of the original function, then we found the function of the inverse, and then we graphed it and found that it was symmetric across y equals x. Pause the video for a minute and try this example. See how you do. So when you think about your domain, it's going to be restricted to x where x is greater than or equal to 0 because once again, our function here is symmetric about the y-axis. So to make it 1 to 1, we can just make it so that our domain only includes values greater than or equal to 0. And then interchanging our x and y values and solving for y, we find that the inverse of this function is equal to the square root of x plus 7. So we know that the square root of x plus 7 has to be greater than or equal to 0 in order for our inverse to be defined, since you can't take the square root of a negative number. So that means that x has to be greater than or equal to negative 7. If x is negative 7, the value of our inverse would be 0. If it's any smaller than that, it would be negative, and that's not possible. That would result in an undefined value for our function. So now let's check our work and graph it. So once again, when we apply our inverse to our function and then apply our function to our inverse, we get x both times. And then again, the graph of the inverse and the original function are symmetric about the line y equals x. So it looks like we've done this right. So next we're going to take a look at cubic functions, and cubic functions are actually easier because they're already 1 to 1. So we can basically skip our first step here. The domain can be all real numbers because our function is already a 1-to-1 function. So let's start off by interchanging our x and y values. So we'd have x equals 0.5 y cubed. After dividing both sides by 0.5, we end up with 2x equals y cubed. Now we just need to take the cube root of both sides. So the cube root of 2x is the inverse of our function. So let's talk about when that will be defined. Well, since this is a cube root, the value underneath our radical can be negative, because you can have a cube root of a negative value and that can be a real solution. So there's really no restriction we need to have here. So the domain of our inverse is also all real numbers. Now let's check our work. So when we take the inverse of our original function, we end up with x. And when we apply our original function to the inverse, again, we get x. So it looks like we did it right. Now let's see what our graph looks like. And doesn't this look cool? So again, our functions are symmetric about the line y equals x. So our graph looks good, and it also looked good when we checked our work. Why don't you try example 2, see what you get. Go ahead and pause it, and then hit play when you're ready to see the answer. All right, so we found the inverse of our function here. And once again, we don't need to restrict the domain of the function, and the domain of the inverse is going to be all real numbers because this was already a 1-to-1 function, and its inverse is also defined on all values. So when we took the inverse of our function and then applied our function to our inverse, we got x in both cases. And now let's check out our graph. All right, so we have f of x and we have its inverse. And yes, these are symmetric about y equals x. So all looks good. So let's just review the process that we use to find the inverses of quadratic and cubic functions. The first thing we do is restrict the domain if we need to in order to make our original function 1-to-1. For the second step, we interchange x and y. That means we switch them, and then we solve for y. Next, we have to think about the domain of our inverse. Where will it be defined? If it's a square root, we know that it has to be, the radical value has to be 0 or greater. And then we just check our work and we graph it. And we end up with a really pretty graph where the function and its inverse are symmetric over the line y equals x.